Good morning, everyone. Welcome to our virtual informal systems seminar this week. It's my great pleasure to introduce to you our speaker today, Joao Saude. Dr. Saude received the Bachelor of Science degree in Aerospace Engineering and the Master of Science degree in Mathematics, both from IST University of Lisbon, Portugal. And he received his PhD degree in Electrical and Computer Engineering from Carnegie Mellon University in 2018 under the supervision of Professor Sonia Carr and co-supervised by Diogo Gomes from KAUST. After a period of research scientist at JP Morgan AI Research located at New York City, he is now at the Systems and Robotics Institute in Lisbon. His research focuses on optimal control theory, mean-field games, recommender system, computer vision, explainability of graph neural networks. And today he will talk about mean-field games models on price formation. So without further delay, let's welcome Dr. Joao. Dr. Joao Saude. And the floor
Thank you so much, Fang, for your introduction. It's a great pleasure, and thank you to be here or connected or to you today, and to be talking. And I will be talking about mean-field games, more concretely about some models of price formation. Some of this work, all of this work was done. So a part of this work was done with Diogo Gomes, and another part with Levon Nurbenkian. So yeah, let's start. Let's see if okay. So what are why to study mean-field games? So mean-field games is actually a very good framework to study systems with large number of rational players that act non-cooperatively. This was something was introduced by Wang, Keynes, Malame, and also Lasry and Lyons independently. And there is several applications that you can use MFG for. So for instance, crowd and traffic motion, communications, wireless 5G, algorithmic trading, economic models, power grid management, and I think Keynes and Malame, that I think I saw him here. He was in my PhD thesis defense, so maybe something that I'm presenting here you know already. They contributed in this part also, resources exploitation, biology like chemotaxis, and more recently even multi-agent reinforcement learning kind of things. So there is a vast application. It's not only a theoretical subject, and it basically, or like as a, let's see, as a mean-field game in a nutshell, I would say that if you have a very large number of agents that are trying to optimize against something, so you have a bunch of Hamilton-Jacobi equations, and they are coupled between their each player influences the other on the decisions it takes at each time. So you would have these very big partial differential equation systems coupled, and this is kind of intractable from the analytical and numerical point of view. If n is quite, I mean, doesn't need to be very big. For n like as small as 5 or 10, this is very difficult already. So fortunately, Wang, Keynes, and Malame, and also Lasry and Lyons came to help and introduced mean-field games. The idea here is kind of thinking about these systems, taking the n to the number of agents to infinity. So you kind of have like now a continuous instead of discrete system, and the resulting equations are these two here, where you have a Hamilton-Jacobi equation now that depends on measure m, which is the distribution of players, and a transport equation or Fokker-Planck equation. So this is more or less mean-field games in a nutshell. Of course, there are much more details that I'm missing here. So today I'm talking about first price formation in electricity markets, but this is just an example. Actually, this kind of structure that I'm presenting here as other several applications, including something called something that I saw recently, a paper using this kind of models on when you actually price impact models, when you actually want to sell a lot of stocks. The structure is more or less the same. And this first part was done with Jogoms. The second part, I'm going to talk about non-local infill games. I will explain why this is here, but this has to do because with non-local infill games, I want to explore prices that not only depend on time, which I did, I'm going to show you on the price formation electricity markets, but also on space. So let's start. So the main motivation why we started to study this was that actually there are some works out there where namely by Kizil-Kale, Malame, that you can store energy as heat or cold using space or water heaters or air conditioning. Like if you consume more during when the energy is cheap, and store and heat warm up water to use when energy is more expensive. So you are kind of storing and energy, right, as heat. But also when you have a lot of batteries connected to the network, like the electric cars, we can also do that now. This problem was firstly studied by Paula, and they actually came up with some algorithms that study this mean field game system, but use like a tabled price, right? We now wanted to to see if we could find like a structure, like an infill game structure, where we can find actually the price is not fixed, but the actions of the player will determine a price. So kind of the price would be some sort of equilibrium of. Sorry, I cannot. Okay. So what's the model? So let's start for the simplest case, the deterministic case. And so each player has a battery, okay, that is connected to the network. I'm sorry, I don't see your faces, so please, if you have any question or if I'm going too fast or too slow, please just let me know. So each agent has like a battery that is connected to the network. And he can control the battery, the dynamics, and the dynamics is given by x dot t is equal to this alpha t, which alpha is the control. So he can either buy electricity or so consume electricity from network buying, or sell the electricity. So actually provide the network with the electricity that is in this battery, right? So the electricity cost is given by pi. And the consumers can actually do some kind of arbitrage. So they can sell, store, and the electricity, right? So each agent has a running cost, which is this L. It's given by the price at time t times what they are doing. So if they are consuming, this alpha will be positive. Sorry, cost. So this alpha will be positive, so they are paying a cost, right? So they are paying the price times how much energy they are consuming. They are taking from the network. L0 is another kind of cost that do not depend of the price, but just to be just to have something not so general and to think about something. Let's think about L0 as alpha square, which means that the more you consume or sell, because when you charge or discharge your battery, the more you do this, you will degrade the battery. So this is kind of a penalization for doing this too much. And this C, it accounts for the batteries wear off, and is actually a preference for you. So this can be chosen, right? Is a parameter. This potential V actually gives you constraints on the battery charge. So you don't want to, for instance, decharge too much the battery, or you don't want to overcharge the battery, because in these regimes, the battery degrades or something like that. So this is something else you can choose, and depends and accounts for this kind of controls on your battery. So you don't want the battery to be depleted or to be near maximum capacity, for example. And then, so you have a cost functional. So I'm considering here a finite horizon time, finite horizon time problem. So which is given by this integral starting time little t, terminal time capital T. L is the cost, and ut is the terminal cost. That can be, for instance, you don't want. It can be something you can specify. The value function is the infimum, because this is a cost. So you want to minimize over all strategies or policies alpha, suitable, measurable, and all these usual assumptions. The Hamiltonian is given by the supremum of the Legendre transform of L. Sorry, this should not be L0, should be L. Actually, it's L0 because L. Let me see, L. No, L depends on alpha, so this is L. Sorry. Now, like from standard theory, right? You can write your Hamilton-Jacobi equations, which is minus the derivative of the value function with respect to t, even if it has to be in some more generalized sense, viscosity solutions or something, but I will just write it like this, and plus the Hamiltonian equal to 0. We have the terminal conditions, and the optimal control, it's, if you look formally, right, you take the supremum over A of here, and you get this. So the optimal control is minus the derivative of H with respect to P, which is this part. So var P plus the derivative of U, so with respect to X, which is the value function. And when agents follow this strategy, right, they give rise to this transport equation. So every player is following the same strategy, and so you have the transport equation, which is the derivative of m. M is a distribution of players. So m gives you how many players are. So gives you how many players are distributed in X, and X is the state of the battery. So kind of you have to start. So the initial, the mx0 is kind of what is more or less the state of the batteries at the beginning, right? So how many players have batteries with certain charge. So then you have, let me just refer this. This is not really a mean field game as we are used to, right? Because if you see here, the Hamiltonian do not depend on the distribution on M, right? Because you don't, in this case, what you want is that you don't want to solve a problem where each player needs to know what is the state of the batteries of the other players, right? What they need to know is what the price is, and that's what you have here. So, and how is the price given? The price actually, it's given such that the demand and the supply balances. So this is in the grid is quite natural to think, right? You know, if you are putting too much energy into the grid and no one is consuming it, you can kind of burn the grid down, right? Because you're injecting too much energy in the grid. On the other side, if you are injecting too little, then you can have so I mean now you can have blackouts, right? So you don't. I forgot the word. I'm sorry, but if you don't have enough if you don't have enough energy, there's the grid shuts down, right? Not energy supply, not energy to supply the grid with. So so this is kind of a natural request to do. So the balance of the supply and demand, Q is the demand, and alpha is the supply. So alpha, you have to integrate these over M, which is the distribution of layers, and alpha is what they are doing. Either they are selling or buying, right? And this needs to match. So as we saw before, the optimal control is given by minus dph. So we get this constraint, which is, and this constraint determines the price. So because if you change the price, you will change the behavior of the users, right? And then you can change the price such as these matches. So that's what you want. That's what you want to find. What is the price that does this and originates functions so that you can solve all of this. So the system you want to actually solve is this. So you have this Hamilton-Jacob equation, the transport equation, and the link between the two. Now it's given by this constraint where you require that offer and demand matches. So you have the initial and terminal conditions as usually in a mean-field game. So T is the constraint, right? Final constraint, and M0 is the initial distribution of the agents. Okay, so we can complicate this further if we consider that the dynamics is actually stochastic. So before we had x dot equals to alpha dt, but if you have also some kind of noise, some kind of running motion, you have this SDE, and in this case, the system actually what we get is this one. It's the same, but we have these terms here, extra terms, and initial and terminal conditions are the same. So under some assumptions that I will just keep it, and many pointing, I mean, under some assumptions there are not so many that restrictive. It's kind of natural, like Lipschitz and some concavity or convexity. So under these assumptions, you actually have this theorem that is, there is, so the first 5 assumptions give you, there exists a solution, there exists a solution, pi, so of that constrained mean-field game, and U is a viscosity solution, because now you have this kind of decoupling between these two. It's only coupled by bar p, which is this final equation. So Lipschitz and semi-concave in X, okay, these are just some technicalities, differentiable almost everywhere. And var p is Lipschitz continuous, which is kind of good for price, right? Moreover, if epsilon is bigger than 0, so we have more regularity, right? In these cases, so we can prove the unicity of solutions. If not, then we need an extra assumption, which is the V and the terminal cost, U are convex. So even in this case, then we have a unique solution, um bar p or pi, sorry. Moreover, U is differentiable in X for every X, and U second derivative with respect to X and M are bounded. So I'm not going to the details of the proof of this theorem, but the first part, it's kind of follows more or less the same. You have some semi-concavity estimates, and you have some, actually it's a little bit more involved because you need some compensated compactness arguments, but more or less follows the mean-field game kind of solution, how you prove existence. And unicity follows the monotone method. Actually, it's easier in this case, but I'm not going through it. I decided maybe it was a little bit too boring. I'm going to talk a little bit more about the model. Actually, I'm going to give you a concrete model. So if your L is again the same I presented before, so we don't have a potential now. So you penalize using too much your battery. So charging and discharging, you are penalized by this alpha square. Then your cost depends on the price. So if you sell, this is negative and you gain money, so your cost goes down. If you buy, your cost goes up. This is positive. Okay. So the corresponding, it's easy. You just plug it there, so you get this model. You can actually, the good thing of this model is that you can actually get a closed form solution for this model. It involves a lot of integration by parts and a lot of trying to find constants that are preserved in the differential equations. But it's kind of easy to follow. And you can actually find, we actually found that the price in that case for that cost, right? It's given by these simple equations. So you have like this constant theta minus C, which is the so C you define is the users define how much they care about their battery. QT is actually the supply at the moment. So the price is linear, and actually I will show you then after. We used Q as a historical data, and you can see that this matches really closely to what really happens. We use real data.
Sorry, I have a quick question. So the dynamics that you are considering to obtain this price process, is it deterministic or stochastic?
Oh, so for this, this one is the first order mean field game. So you see, you have the 0 on this side. So it's not a stochastic.
It's deterministic.
Yeah. Sorry.
Right.
Yeah. Thanks for pointing out.
Thank you.
Yeah. So in that case, you have the solution for the price, and it's given by this. So if you now instead consider a terminal cost, that is this one. So actually you want to finish with your battery not deviating from some. So the battery X is the fraction of your battery from 0 to 1, right? The charge. So you imagine that you don't want to deviate from the middle, from 0.5. Then at the end, so I'm solving this from it's a finite horizon problem, and at the end you want your battery to be at that state charge, right? So you can also solve this kind of problem. The solution is also pretty simple. It depends on this K0 is the integration of how much the demand actually. So remember, this QT is a function that it's given, right? It's the supply. Sorry, not demand, the supply. And yeah, so this is also, you can also easily find a solution in this case. So another case which is a little bit more involved is when you have a potential. So when you actually don't want not only at the end of the at time t, capital T, right, but along all the time from 0 to capital T, right? You don't want to, so you don't want to deviate for some, I mean, you don't want your battery to go, for instance, to 0 or for instance to 1, right? This is a quadratic potential, and you are penalizing this kind of behaviors on your battery. Okay, this the system is again it's this one here, right? You just plug this this kind of running cost, and you yet again you can also find a closed form solution. Again, involves a lot of integration by parts, and actually involves Laplace transforms somewhere in the middle. And this is the only catch here. The difficulty here is that you have to actually approximate your data that you use, your historical data, for instance, and you have to approximate it by functions such that inverse of the Laplace function exists. So that's but otherwise it's a closed form solution, which is kind of for me kind of, I mean, yeah, it's kind of surprising in this kind of equations, and a little bit unexpected. Yeah, so as Dina was referring, I'm just considering here the case of the deterministic case. Yeah, for the other case, actually proving existence and the unicity is actually easier in the sense that you don't need so many that extra assumption, the sixth, but actually it's, I mean, it's, I could not find a closed form solution for that. Of course, to solve that system, maybe I could not, we could not solve that system in a closed form, to find a closed form solution for that system, but numerical methods, for sure, would be a good, there are some numerical methods that would work. Actually, I didn't look into them, but I'm sure that there are, or maybe if not, there is a good research direction, maybe. So let me show you now some price formation. Now we're using real data. So we took some power supply from UK in a 24-hour period. And this is more or less what it looks like, right? You can see that, of course, during the day, the price varies in time, and you have some peaks here when people wake up and go to work, or when people maybe, I don't know, get home at around 8. So what we did was we compare our price formation model with some with a mean field gain model presented by Paulo, actually. So their model, the price is exogenously given. So the price is set, is a table, you know, like if people are consuming this much, the price is less. Of course, if people, like when I say people, like the whole country is consuming more, there is more demand, aggregate demand, it's bigger, then of course the price will go up. So we have this peak. So something, of course, I'm sorry. Okay. Of course, the price will be bigger in, I don't know if you see, but like around 20, right? Or like 8 p.m. will be bigger. And of course, like at 4 a.m. will be smaller. So, but this is not the price, this is the supply, but so they use a table that would give you how much gigawatts are they consuming, and then the price would change in that table. And then they solved the mean field gain. So not this model, but a mean field gain model where the price is given, not where the price is. It's computed. Actually, it comes from the equilibrium, and I will show you I will compare in a minute. So, but before that, I just want to talk about the C, right? The C is that constant that you need to specify, right? So, of course, they did like in their paper, they don't have this C, and you had to empirically estimate it or calibrate our model against their model, so we could compare our results, right? So our price now I'm looking into the simple case where it didn't have the potentials. We just, because that's the setting they use. And in this case, we actually just did like a least squared approach to find the C. N is the number of agents, so N is the number of batteries connected, because then you have to specify. This is 1 million batteries. This is what they used, and we obtained the C, which is like around 0.20 cents, which is, we talked to some people, and actually this is a very good approximation estimation. So these are in line. So this is how much you care about. This is how much you care about damaging your battery, right? That's the constant there. Okay. So with this, so actually you see here, so in green now, it's the price, the dollar per megawatt hour in time. Like, so this is a 24-hour period, and so the green line gives you like it's the price that you can go to the table and read. The price is a function of the aggregate consumption, and it looks like this. Okay, so in blue you actually see the model Paula and all followed. So they follow that price, right? And they computed this blue line. They used a iterative numerical method to compute this. And so this blue price differs from the green price because in the green is when you have all the system, right, the data, and they don't have the batteries, right? Now you see, okay, if I plug these 1 million batteries that can actually store energies and sell when the price is higher, you would have like this stabilizing effect on the network. So the price is a little bit upper here when the price is low, so people consume a little bit more because they are saving the electricity, and then they sell at the peak, right? And here you can see as well. So of course these 1 million batteries, no, I don't know, but it's about like 10% or maybe a little bit less, like the aggregate storage that you have with these batteries is not that big comparing to what are being produced. So that's why you don't have a lot of. If you put more batteries, maybe this thing would be different, of course. And in yellow is the price we compute by that simple function. So and it's a closed form solution, and you can see that is pretty much makes sense. What we get, it's pretty much follows what people do. But our price is not a table price; is a price that actually comes from this Nash equilibrium of this mean field game system with constraints. So yeah, so it's but it's doing what it's supposed to do. The price is going up when the consumption is going up. Of course, it's linear in that thing. But the good thing here is that we didn't need any numerical method to solve these kind of things, and it comes. It gives we get a closed form solution. So what are the possible extensions to this? And that's why I'm going to talk about non-local things is, so this price formation, we can prove the well-posedness of the problem and develop a method to compute the closed form solution. Our model has minimal number of features, right? Only the C that you have to find somehow or define, and really fits well the data, and n, which is the number of batteries, right? Okay, you can see some stabilizing properties of the price at peak consumptions as before, but the main difference here is that previous methods rely on tablet prices and heuristic numerical methods. Here we could like prove the existence, uniqueness of solutions, and in that specific case, when you choose the same cost function as the other models, you actually found a closed form solution. Of course, it would be interesting to study different cost functions and see what we could obtain. Also, another interesting model would be, so suppose that these were cars, right? Cars that are connected to the network, they have batteries, but of course people need to move. And when people move, they disconnect the cars. And so if they disconnect the cars, of course, the number of batteries will change over time. And we wanted to maybe to study what would be the effect of the price in those behaviors, right? If you increase the price, would people leave the cars connected or not? I mean, at least to have some sort of, so we would like to explore this kind of two states model. So the first state is the dynamic as before. The second is you are only consuming. So you have lambda, maybe a constant, maybe not, but you consume the battery, and you have this kind of model, and would be interesting to study this type of problem too. Other interesting problems here are when the supply depends on the price. So this would arrive when like you have more supply if the price is bigger. This is something that would arrive, for instance, in the stock market, right? Because if the price is bigger, you have more supply, so you have maybe people willing to sell, or if the price goes down, maybe you have more people willing to buy. So the supply here, in that case, will depend on pi. This would be an interesting problem, and the supply and demand in this case also fits very well, right? Because that's exactly what happens in the stock market. Is the price is defined whenever that condition is satisfied.
Well, that seems to be extremely interesting, an important case. Did you have some preliminary results on that?
More or less. So the existence is actually similar. So you can actually prove the existence for in this case, and the uniqueness as well. So I didn't see if I could solve this kind of problem like analytical, or have a closed form solution. I would have to think, but the existence and uniqueness follows similarly, actually. So provided that this thing, it means that provided that the supply goes up when the price goes up. But
completely reasonable. I just wondered if you had any initial results on the dynamics that you get from this situation, and definitely the partial dq dw bar or omega bar is a completely reasonable hypothesis. I just wondered if there's any dynamical consequences that have appeared yet.
So I didn't look to that. I mean, I didn't study that part. I just saw that, oh, this might be important, but actually this follows. I know for sure. I verified the existence and uniqueness follows for sure. I didn't have any other results to part of this actually, but that's why I would say that it would be a good future work, maybe. So okay. So another model to consider would be when Q actually depends on delayed prices. So actually the market doesn't adjust immediately. So there is a delay. The price doesn't, and this is more realistic, right? The price doesn't immediately change, adjust to the supply doesn't immediately change to the price, and vice versa. So this probably should be a good case to work. Also, when Q has actually random fluctuations. So imagine that Q follows some stochastic, some ST or some random fluctuations. This is probably relevant in the case of energy production from renewables, like solar. Solar is a little bit more predictable, but maybe wind, it's not so much. I don't know. So another interesting case, that's why I wanted to talk. I don't have a lot of time, but I will try to be a little bit faster, is what if Q actually depends, okay, imagine that Q depends on time, but also depends on space. So for instance, a situation with this arrive would be, for instance, riding like Uber, for instance, right? Uber, like prices its tariffs, right, in time. So it depends on the time. If you order Uber from your home, of course, the price it depends on the destination. Okay, but if you order a Uber from your home to the same to school, which is the same destination, it depends on the time of the day you order. And of course, if you order from some other place to the same location, it also varies. So it's very straightforward to understand that the price can also depend on the place you are, right? Not only on time. For that, we wanted to study some other problem. Okay, sorry with me, because since I don't have a lot of time, I just go here, and just to explain, I can actually use this one. I'm sorry. To explain that this Q would depend on X, right? And this pi, which is the price, will depend on T and on X. But if you have like a system like this for the case of Uber, right? You would see that actually you would get, so cars that are very far away from one point will go, the gradients will go to where the price are bigger, right? But this is not really something that you want, because you don't want drivers to be very, very far away, right? And then because they see a pricing surge in some downtown, but they are very far away from downtown, they will go just drive just down there if they follow if that's what they want to go to where the price is bigger, right? Because this is like some problem that people that study this, and there's like plenty of papers that refer a lot of solutions. You get cars coming from very far away just to try to chase the surge, but in real life what happens is once you get there, the surge is no longer there, and then you are chasing these big prices, and it's not the optimal solution anyway. So again, so the agent's dynamics is the same, x dot equals to v. The Lagrangian now it's a little bit different. Why? Because we don't, in order to do to not have this, or in order not to have like cars coming from very far away, what you want is actually to give what you want is that agents in certain areas really prefer and really look to what is happening in their neighborhoods, right? So you have this kind of non-local coupling. So this kind of function, which is so here it's not connected to the price yet because this is a separate work, but this is some kind of future work I think is very interesting, is to blend these two approaches. So these non-local coupling, so what you have is the kernel. So these are examples of the kernel here on the right side. And then what this term makes is that agents are like more concerned to what is happening on their neighborhood than elsewhere. So you can see agents are more. So this is like, you can think about this as where the agents are looking for. Of course, if you choose a flat kernel, then the agents will consider everything, and we'll see some numericals on this. So since I'm having not much time, I will So of course, I will skip this quite fast. So, but the thing is, okay, you use Fourier expansions to try to study these things a little bit better. So of course, so what are important here is that we consider these separable kernels. Okay, as you can see, this type doesn't work for everything, and then your non-local mean field game is of this type. So we have this extra. It's not zero anymore. We have this extra term, and this is the kernel, right? The kernel that gives you. So this is just a little bit of computations, and actually just defining some quantities, because I wanted to go through this, but maybe I will not have time. So let me just, sorry, because I have, okay. So let me just go more or less fast. So the idea here is actually to use the Opflax formula. Actually, the Opflax formula gives you a solution, a characterization of the solutions of these type of equations. So, and these type of equations that have, I mean, Opflax formula also exists for the other case, but maybe it's not as useful as in this case. So we can define we can find the optimal trajectory. The optimal trajectory, it's like the optimal control before, but it's a little bit a different setting here. Anyway, you can actually so Opflax, instead of try to solve an equation, right? You solve the partial differential equation. You solve directly this variational problem here. So in order to find the u, okay. So the main result is that actually you can, in this case and in certain conditions, and for the kernels that are positive, definite, and symmetric, you can actually see that the problem 3, so the equation, the equation above, the equation above is actually you can solve it by this convex optimization problem. And this is really good because this is really fast to solve. I'm not going through the numerical method, but what we used for primal dual hybrid gradient method. And I'm going just to show you some results. But the main properties of this numerical method is actually that it's actually very fast, and it doesn't it's curse of dimensionality free, because actually you can choose. So this is kind of you can think about a little bit of a particle method filter, and you can actually, so the complexity of the method actually goes with these particles. I'm trying to see if I can show you. It goes with this R that you choose, which are the trigonometric functions that because of the kernel, Fourier kernel, and also the support that you choose. So how the discretization is going, but it doesn't explode. Okay, because you actually follow the particles, and you don't have to discretize all your space, but you discretize your measure in the beginning, and then you follow the optimal paths. So you don't have to discretize the whole space. You just have to follow this push forward, which is this given the push forward of the initial distribution with these optimal trajectories that you can actually solve with that convex problem. Okay, I'm sorry for being so not precise, but just let's see how this works. So if you have initial distribution of players, you see, and a terminal cost function, this I'm just considering 1D, but I will show you in 2D. And then you have the kernels here. So the kernels is remember, right? How the agents react, right? So if you have a kernel, so this sigma is actually the spread of the kernel, right? If you have a kernel that is actually flat all around your state space, right? Users actually are indifferent for, I mean, not indifferent. They give the same weight to what happens near them or far away from them. So this is the situation where the cars will chase the search in the whole city, right? They see where the price is bigger in the whole city, and they just go there. So in this case, in the second case, which is this kernel, this is okay. So on the top you have the kernels, on the bottom you actually have a section of these kernels, right? So you see that the blue one really cares a lot what happens very close to him. The blue one not so much, but more than the yellow one for sure. So here for each kernel, so these are the sections, right? So what we have on the bottom on the trajectories are actually the trajectories of the agent. So this is how you discretize your measure. So you can actually choose, right? So imagine that you in D, like if you look to the first one, so let's say first column, second row, you see that I choose a discretization of the measure of the initial, right? Of the initial M0, right? I choose a uniform there, and I don't have to discretize the whole space from 0 to 1, 0 to 1 squared, right? I can only put, I put some particles there, and then I follow the flow, the optimal flow actually, and that's what you have. So you see here that, so let me see what I put. So, okay. So here is the terminal value, and the terminal value function. So here, so is the cost, right? So the terminal, so the lower cost is here after 0.2 and a little bit before 0.8. And you actually see that the particles go there. So the agents want to be there, right? And so in this kernel, which is bigger, so they separate more when they travel there. You see, and in C you actually have the Econol equation, and that's the solution for the Econol equation. They are straight lines from whatever you are to the minimum. Okay. So this is the density now, but in 3D, right? So you have X and T, and then you have the density. So you see the initial distribution, and then you have these spikes is where they congregate, right? But here they don't like to be next. They are avert. They don't like to be next to each other. So there's more space here. They just follow the straight lines, and they don't care if they are close to other ones or not, other players. So I only have 2 minutes, but I will be very fast. So here I did the same thing, but now in 2D, because this is so fast, and it really works in 2D or in 3D. So here are the kernels. So again, I use more or less the same. Here you have the trajectory. So it's the same spirit, but now just in 2 dimensions. And so X is 2 dimensions, which is like a city, right? So you see in the first row, you have the trajectories when K is flat. You see this is the Econol equation, and this, the trajectories are straight. Here they try to avoid, is a little bit messy here, but at the end they congregate in the spikes of the or in the valleys of the cost function, because you want minimum cost. You see, you have 3 here, and they congregate along. So these are kind of oblique things, and you see that these ones congregate much more, and these ones they don't like to be so close together, so they don't mind to pay a higher price of being along these valleys, but the cost here goes up, but they are not so close together. Okay, So yeah, so now the things I'm working on is this part, is to how to actually assemble these two things. So non-local costs with non-local meaningful games with constraints. So in order to apply this to type of Uber and try to find equilibrium prices in these cases, and avoiding that crucial thing of not having cars coming from far away, because this is really no, I'm not saying that it's difficult, but it's something that they really want to solve. Yeah, and I think that's all. And thank you for your attention, and please let me know if you have any further questions or clarifications.